We're going to revisit Leibniz notation for just a minute because I've been telling you that it's a notation that's super useful in all areas of calculus. We saw how helpful it was on the derivative end of things, and it's equally as helpful, maybe even more helpful, on the antiderivative or integral end of things. So Leibniz notation models the extremely small changes in x and y that occur when using derivatives. We know that dy for us really is just tracking tiny changes in y, which is what that notation means right there. Here, dx means tiny changes, infinitesimally small changes in x. So when we talk about differentials, which are dy and dx, as opposed to the derivative, which is dy over dx, then we're really talking about two different things. So remember, fundamentally, we can only use the idea of derivatives because we can change the position of one point on the secant line and bring it very close, infinitesimally close, to a corresponding point on the tangent line. And we want the change in x and the change in y to be infinitesimally small. So here's the definition of differentials. If I have a function y and it equals f of x, where f is some differentiable function, the derivative exists everywhere, then the differential dx is an independent variable. So dx can be given a value of any real number. So if it's a variable, it's a placeholder for a number. The differential dy is defined in terms of dx, in that since we know f prime of x is dy over dx, then when we go from the derivative to differentials, we can multiply both sides by dx, and what we get is we go from the derivative to differentials. We get that dy therefore has to be equal to the derivative times dx, and those are differentials. Dy and dx are differentials. So if dx is given a specific value and x is given a specific value from the domain of our differentiable function f, then the value of dy, the slight change vertically in the value of our function, can be determined. And if we know how to calculate derivatives, we know how to calculate differentials. So for instance, if we were given this example, y equals the quantity 2x plus 3 all raised to the negative 4 power, and we were asked to find the differential dy, we know that dy is the derivative times dx. So the first step is we would find the derivative. We would find dy dx. That's a chain rule problem. The negative 4 pops down front, reduce the power by 1, times the derivative of what's inside. So we could clean it up. That's negative 8 times the quantity 2x plus 3, all raised to the negative 5. Now that's dy dx. It asks for dy. Well, the difference between the derivative and differentials is multiplying through by dx. So this dy is negative 8 times the quantity 2x plus 3 to the negative 5th power times dx. There is dy. So let's look at another example. Here we have the function y equals f of x, and our function is x cubed. We want to find the value of dy in each of these cases. So if we're given an x value and a dx value, we can find dy. So again, the first step we're going to do is we're going to find our derivative. Our derivative is dy dx, that is 3x squared. The next thing, we're going to find our differential. That's 3x squared times dx. If I have an x value and a dx value, I can find dy. So I have dy equals 3 times, here it tells me x is 0.5 squared, and it tells me dx is 1. And again, I don't have to simplify. Here is the same function, and I've already found the differential equation. So again, I'm going to plug in the x value they gave me and the dx value they gave me, and there is a numerical value for dy in the case of part B. This is how we find our differentials from our derivatives. We know these derivative rules, so we know how to find derivatives, and we can use that to find differentials, because all differentials are our derivative multiplied by dx. And so if you compare what's happening on the derivative column with what's happening on the differential column, you'll see that the rules are very, very close to one another. All right, so we know how to find differentials if we're asked to. What is a differential equation? We know that we start with the derivative, we multiply through by dx, we can come up with our differential equation. So what is it? What's the power of it? Why do we need to know it? It is the most important application in calculus. The differential equation is what gets you from the derivative function back to your original function. It is the function that tracks the tiny horizontal changes, dx, and has them related to, with the equal sign, tiny vertical changes, dy. It's a very, very powerful application for integral calculus. So to solve a differential equation is to find the unknown function portion of the differential equation. Again, just like I said, if we start with the derivative function, it is our way to work our way back to the original function f of x. These differential equations model real-world behavior really closely. Now again, we live in a three-dimensional world, and I recognize that, all of these problems are very contrived problems because they're two-dimensional problems. But if we are on our way to learning the mathematics of how we're going to model things in the real world, this is a very big first step. It's foundational. Differential equations is all over the exam, and you know what that means. So it shouldn't surprise us that in real-world problems we notice that changes occur, and we want to predict future behavior on the basis of current changes. So let's work an example here. Find the xy equation of the curve that passes through the point -1, 2, and whose slope, what is that? dy dx, at any point on the curve is equal to twice the x coordinate at that point. Well, there's a differential equation right there. It gives me a differential equation in words, and it gives me a point that is on the function f. It tells me f of -1 is 2. And we'll see with more and more examples that we do, we'll see the importance of this graphically as well as analytically. Let's talk about how we find f of x. It wants the xy equation. It wants us to find y equals f of x just given this information. Well, I know that this is a differential equation. I know that I can multiply both sides by dx, and look what's happened. I've actually separated my variables. Separated my variables. Everything that has to do with y and dy is on the left side of the equal sign, and everything that has to do with x and dx is on the right-hand side of the equal sign. And as long as I do the same operation on both sides, then that's a legal mathematical move, right? Same operation on both sides of the equal sign. Well, I want the antiderivative. So I'm going to integrate this side and integrate this side. That's legal for me to do. If dy equals 2x dx, then the integral of dy must equal the integral of 2x dx. So let me give myself some space here, and let's integrate this. The integral of, basically this is 1, right, with respect to y. What did I take the derivative of with respect to y to get 1 for an answer? Well, that was y. And now I'm over here on the other side of the equal sign. So I'm going to pop my constant out front. The antiderivative of x is 1/2 x squared. And I need my constant of integration. And you say, well, why isn't this y plus c equals x squared plus c, because I only need one constant of integration. If I take this constant and I move it, using good algebra, to the other side of that equal sign, I still just have one constant of integration. So we don't put it on both sides, we just put it on one side, and it's really handy to put it on the side where your x is. You want to solve this completely for y equals. Now remember what we have here. This is the family of functions, family, whose derivative, right, equals 2x. They want me to find the specific member of the family that contains the point -1, 2. Remember, they tell me f of -1 equals 2. Well, there's only one member of this family that contains that point. This anchors me in the plane and lets me pick the one single family member that contains this point. So let's put some terminology with that, okay? When they give you a differential equation, which is what they've done here, when you get to this point right here, this is the general solution, and you need to know that. You're going to have instructions that say find the general solution to the following differential equation. So you're going to need to know what general solution means. When they give you a point like they've done here, when they tell you f of -1 equals 2, this is called an initial condition. That's terminology you need to know as well. They will give you the initial condition. And once they give you the initial condition, you can use that, because this is f of x equals y, right? This is an x, y point in the plane that you can plug into your general solution and get the specific solution. I'm right here at the end of this video, so I'll stop here and we'll pick this up in the next video.